All right. So yesterday we did the shortcut method for net ionic equations. Know your rules. Maybe I just need to make the pen work. That would be good. Know these rules. And we are actually going to do these one more time. You've already got them done from yesterday, but let's practice again. Aluminum metal is a solid, so we just write aluminum as a solid, and it's still not working, plus, okay, I'm not going to record this period. I'm going to try using my finger. That could be a battery issue. Let me erase and see. Sorry, those at home, having some technical difficulties. Yes, it is probably the battery. Who said that? Good job, Isan. Nice assumption. So we'll do that. Aluminum solid is added to a solution. This is telling you that this is going to be in ions. Silver nitrate is soluble. Therefore, in the old way, we would do net ionic equations. You would have taken it split into ions after writing AQ next to it. So what do we actually write down here? Just the Ag plus. Why don't we write down the nitrate? Because it's always soluble. So we go to the metals now, and we need to make something go up and down. This being a single replacement reaction means it's redox. So something has to go up and down. Go to metals first. Can you make something go up? Which one? Aluminum can go up to +3, and what does silver do? Go down to 0. All right? Small chunks of sodium, that's a solid, so we don't write it as an ion, is added to water. We have to balance. Thank you. I'm trying to rush and catch up. So in the previous problem, we do have to balance because we have a +3 on the right, so we need 3 pluses on the left. But doing that messed up our silvers, so we need to balance that. All right, this is one of our push-up problems because it's a metal added to water. And whenever we add a metal to water, how do we want to write the water? HOH, so we can see that single replacement of what's actually getting booted out. And that's hydrogen gas. And then our product is sodium hydroxide. Sodium hydroxide is aqueous all the time because it's a strong base. So you would have written it how? Na plus and OH minus as ions. These problems are usually worth 3 points for each problem. So if you don't split up the NaO and OH, you would not have gotten both product points. You would have only gotten one. This has to be split up in ions. Okay? Go ahead. Who says? Right, but you don't cancel it out because this is an ion and this is a solid. So they're not spectators. Chlorine gas, Cl2, is bubbled into a solution of Br minus. So if we're looking at this, why didn't I not put down the sodium? Am I forgetting to balance everything? Yeah, so I forgot to balance the last one again. Ugh. So 2 H's, 2 H's, 2 OH's, 2 OH's. Our atoms are balanced, but now our charge isn't. So if I put a 2 here, I get to no charge on the right side, but that messed up my sodiums, so I need a 2 there. Okay, so now let's try. This is going to be a great video. I'm so excited about this video. Started out fantastic. All right, Cl2 plus Br minus. Single replacement reaction, so this has to be redox. The sodium is not included as a solution because it's an ion. So looking at that, can I make something go up in charge? Bromine can go up to a 0. And what is chlorine going to do? Down, and then we need a 2 and a 2. Okay, magnesium turnings. Turnings mean solid, are added to a solution. Iron 3 and chloride, they're not part of the rules of never write down. They could potentially be solid, make precipitates, we don't know, so we need to write them both down for the moment. Now we need to see what we can make go up and down. This was already a problem when people were doing their homework. I think it was number 3. They're like, I don't know what to do. Go to the metals first. If you can make a metal go up and a metal go down, that is it. And it doesn't have to go up or down to 0 necessarily. Like if I have iron 2 and you have to make iron go up to make it work, can iron go up? Yeah, it can go up to 3, so you can go up from a charge to a charge. Whatever you can do. So magnesium can't go down. It has to go up to a +2. And what's iron going to do? Go down to a 0. Did I need chlorine to get there? No, so we take it out. It's gone. It's not part of the equation. It's there. It's just spectating. It's not part of the redox. So now my charge is not balanced. I look here and I see I could have a common factor of some sort of 6 electrons maybe. So I'm going to put a 3 there and a 2 there. So now I have to balance ions, 2 and 3. Are we good? So that was yesterday. Today we're just going to start working on some different kinds of problems. Addition reactions, for the most part, are really, really, really simple. You're adding 2 elements. You're smacking them together. There's no water involved. You're not making ions. You're just taking 2 elements, solids, putting them together in the form of usually an ionic compound. And its formula you're going to know because you know how to name ionic compounds. So looking at this first one, calcium metal is heated strongly. Calcium metal is heated strongly in nitrogen gas. This is a very standard synthesis or addition problem. We're just going to put those 2 together. Solid calcium is sitting somewhere, and they're passing nitrogen gas over the calcium, and we're going to make, what's the name of the compound we're going to make? Calcium nitride. What's the formula? Guys, what's calcium nitride's formula? Thank you. Ca3N2. So all I need to balance this is a 3 there. That's how simple they are. You're just putting them together to make their ionic compounds. All right? Now, a strip of magnesium is placed in a flame. Mg. What do we do when we put something in a flame? What are we adding? Oxygen. So if we smack those 2 together, we make magnesium oxide. What's the formula of magnesium oxide? MgO. To balance that, I need a 2 here to get the oxygens balanced and a 2 there to get the magnesium balanced. So those kinds are pretty easy. Where we run into a little issue is with ones like these. This is magnesium oxide added to carbon dioxide. So let me just write this down. Magnesium oxide plus carbon dioxide. When students see this, they want to do weird things. They want to try double replacement and do all this weird stuff. No, this is an addition reaction. How do you know that? Well, what I want you to do from here on out is when you see reactions with oxides in them, oxides, period, they're very, very weird. So tell yourself oxides are weird. You see an oxide, I want you to slam on the brakes. I want your heart rate to go up because you know you got to do something. Something's not right. What's the deal with oxides? Oxides are fake acids and bases. Metal oxides are fake bases. The only thing they're missing to become an actual base is water. So if I throw a metal oxide in water, I make magnesium hydroxide. If I throw carbon dioxide in water, that's a fake acid without the water. But if I put water in it, it's going to be carbonic acid. So oxides are going to usually act like acids and bases. And if water is present, they're actually going to be acids or bases. All right? So I have a little saying that I made up. No acid, mo base. Non-metal oxides are the fake acids. Metal oxides are the fake bases. Okay? So you might get problems that are addition problems where I add a non-metal oxide to water. What would you make? An acid. If I put a metal oxide in water, you would make a base. Those are addition reactions. You're taking 2 things and making 1. Another type of addition reaction is adding the non-metal oxide and the metal oxide together. And this is kind of cool. This is a fake base plus a fake acid. What does a base plus an acid always make? Salt and water. But what are these guys missing from being real? Water. So what do you think they just make? A salt. That's it. You get together, you shove them together, they make a salt that contains magnesium, a carbon, and an oxygen in a formula of something you already know the name of. Magnesium carbonate, exactly. So it's a neutralization reaction without the water. But you've got to recognize that these non-metal oxides and metal oxides are fake acids and bases. This is where acid rain comes from. Out of all of these chemical plants, you get nitrogen dioxide, sulfur dioxide, all these different non-metal oxide gases, waste products coming off, you see them coming out of the towers, coming off in the sky. And when rain hits them, you're making acid. And that is where acid rain comes from non-metal oxides. Okay? So is that balanced? Yeah, and that's how you know you did it right. If you can balance the equation, you're good. If you cannot balance the equation, something's wrong in your formula. Okay? So solid calcium oxide, what do I write? CaO is heated in the presence of sulfur trioxide. You're going to slam on the brakes here when you see a problem. Remember, these are going to all be mixed up. I'm not going to have a title. These are the addition reactions. You're going to have to recognize them mixed up. So if you see this, you're going to put your brakes on because why? Oxides are weird. You got to think. So this is a metal oxide and a non-metal oxide. So it's a fake base plus a fake acid. We're just going to make a salt. So what are we going to make? Now, why not CaSO3? I could have made that. There's no way to balance that. If you put SO3 here, you spend a really long time trying to balance it. So the rules are you're always going to make something you know, and it has to be able to be balanced. You're not going to be reinventing new compounds. If you don't know how to name it from your experience from a year of chemistry, it's not what we're doing. Okay? Let me just add one more to this. Let's do N2O5 plus water. N2O5 plus water. Oxides are weird. We're adding a non-metal oxide to water. We're taking a fake acid and adding it to water. What are we making? An acid. Now, the hard part about this is figuring out which acid we make. What are our two possible acids we can make that have H, N, and O in it? HNO3 and HNO2. Check the balancing. Which one do you think is going to balance? 6 oxygens, right? And 2 nitrogens. I'm thinking this is it. 2 hydrogens, 2 nitrogens, 6 oxygens. This is the one. It can balance. It's also based on the oxidation number of the N. So N has a +5 over there, and it also has a +5 over here. Okay? But the balancing trick works too. So the same thing can happen with a metal oxide. If I have MgO plus water, that's a metal oxide in water, which is a fake base plus water. A fake base in water makes a regular base. And what base does magnesium oxide in water make? MgOH2. It's only one kind it can make. And so we just have to balance that, and I think it's already balanced. Okay? All right, so that is addition. Let's move on to decomposition. There could be a list of rules out the wazoo that you can memorize, and I just don't like you memorizing rules. I like you just knowing in general how things work. Decomposition is easy to recognize because you have one compound usually being heated or electrolyzed. Some sort of energy is being added for it to actually just split into ions. Not split into ions. There's no water. Split into elements. Okay? Now, if there is a polyatomic present, what you want to know about polyatomics is they like to decompose to gases, and that's what they do. A polyatomic is not going to split into elements. It's going to decompose and spit out a gas. So imagine a polyatomic spitting out a gas. So we're going to heat magnesium carbonate. Does anybody remember how to do heated in a reaction? Triangle on top. So this is a carbonate. A carbonate is going to spit out a very popular gas. What is it going to spit out? Carbon dioxide. So it's going to spit out carbon dioxide, leaving behind not just magnesium. It doesn't turn into magnesium metal. It actually leaves behind a white powder. What do you think it is? Magnesium oxide. Exactly. So that's balanced. Okay. Now there is a rule that you could memorize if you really wanted to. And that rule that goes with this is metal carbonates decompose to CO2 plus metal oxides. And with my pen, I could have written much smaller than this, which is a little frustrating. Maybe this is charged up again. Okay. All right. Are we good with that rule? So this works for all metals, metal carbonates. All right, potassium chlorate, what's the formula? All right. Now I want okay, I want to go back. I forgot to point this out. In the presence of usually means it's a catalyst. I forgot to go back to the last page. I wanted to change this. Solid calcium oxide, I want you to take this in the presence of off, because in the presence usually means it's a catalyst. So I just want you to say heated with. If you see in the presence of, that means it's a catalyst. So here it's in the presence of manganese dioxide. That is required to get the appropriate activation energy for the reaction to happen, so it's not actually part of it. So when you have a chlorate, remember when we had that series, it was hypochlorite, chlorite, chlorate, perchlorate. What was changing there? Number of oxygens. Oxygens in these polyatomics are very easily decomposed, removed, and added. So oxygen is what's spit out. We spit out our oxygen, and what do you think we leave behind? Potassium chloride, okay? So that is the rule there that metal, I'm going to call it metal halates. This works for all halogens. Metal halates decompose to oxygen and metal halides. Okay, so the oxygens go away. And so to balance this, what do we need? Common factor of oxygens looks to me like it's a 6. So we're going to put a 2 there and a 2 there. Oh, yeah, the 3 would be good to make the oxygens. That's the whole point. Yeah, that looks good. So this last one, don't really want you to worry about a rule. I want you just to kind of think it through. We have solid ammonium carbonate, and it is heated. We have 2 polyatomics there, so each of those polyatomics is going to spit something out. Ammonium. Take a guess. What gas do you think ammonium is going to spit out? Ammonia. We already know carbonate. What does it spit out? Huh? Carbon dioxide. So we got something left over. What's wrong? Yes. Ammonium spits out ammonia. Carbonate spits out carbon dioxide. There's something left behind. Water, exactly. Water is also left. And if you didn't put water, all the elements are represented with just the ammonia and the CO2, but you wouldn't be able to balance it. Impossible to balance. So you need that water. So to do this, we'd need 2 N's, and I think that takes care of it, because that's 6, 7, 8 H's, a C, 3 O's. Okay? So that is decomposition. Say what? Oh, that's apparently I left that off of my PowerPoint for some reason. H2O2 is decomposed. Hydrogen peroxide, you've all bought it. It's probably at home in your cabinets. Does anyone tell me what comes in? A brown bottle. Anyone know why? Yeah, it's light sensitive. So it goes bad pretty quickly too because it rapidly decomposes. So hydrogen peroxide, what makes it peroxide is this peroxide polyatomic where oxygen, it's the one time oxygen is a -1. The only time oxygen is not a -2 oxidation state. So whenever a peroxide decomposes, we're going to spit out oxygen, leaving behind what? Water. And I don't want you to think it makes, a lot of people think it makes H2 and O2. No. Then you'd have little hydrogen bombs under your sink, and that's probably wouldn't be something you could easily buy in the store. So leaves behind water. So don't keep your hydrogen peroxide very long. Definitely not past the expiration date because it'll probably just be water sooner than later. So now to balance this, we need, I guess, a 3 here or a 2. 2 is a 4, that's right, and a 2 here. And there it is. All right, now how do we feel about decomposition? Okay? And again, all of these will be mixed up, so it's going to be really important tonight to practice or over the weekend. So here is combustion. We kind of lied to you last year when you learned about combustion. Combustion was probably something that makes what in your head? A combustion reaction. Carbon dioxide and water, right? That's only the combustion of hydrocarbons. You can combust anything. And all I want you to think about combustion is oxygen smacking onto the elements of a compound. So if you have methane, and I'm going to go through what alkanes you're going to be expected to know on the next slide, but methane is a 1-carbon alkane, so what's its formula? CH4 is burned in the presence of oxygen. What's really happening is oxygen is smacking onto the carbon and smacking onto the hydrogen. So smacking onto carbon, we make CO2. Smacking onto the hydrogen, we make H2O. That's where all that whole CO2 and H2O thing comes from. Okay? So to balance this, I always balance my C's and H's first, and then I do the O's last. 1C, 1C, 2. I have 4 H's, so I need 4 H's. 4 oxygens, so I need a 2 there to make my oxygens balance. All right, lithium metal is burned in air. All you do is smack on the oxygen to the lithium and do an appropriate formula for the compound. There's no water, nothing soluble. They're just smacking together to make lithium oxide. What's the formula? Li2O. So to balance it, you need 2 there to make the oxygens balance and a 4 there to make the lithium balance. So some of these are actually pretty easy. Solid zinc sulfide is heated in excess oxygen. Solid zinc sulfide, you're combusting it when you heat it in oxygen. So the oxygen's going to smack, smack, bam, bam, and it's going to make 2 products. One is zinc oxide. What's the formula for that? CNO. Now the question is, do I make sulfur oxide, monoxide, sulfur dioxide? Start with the dioxides, carbon dioxide, sulfur dioxide, nitrogen dioxide. If the di doesn't work, you can do the mono. But remember, the key is to get this to balance. So we need to be able to balance this. This one's challenging, but it's balanceable. Nope. What? Correct. Well, I'll tell you, everything has a coefficient. This is the answer, so let's balance it. I'm not asking you, is it the answer? I'm telling you it's the answer, so we need to balance it. This with a 3? Okay. So that's 6 oxygens. So if I do this, then I need a 2 here, and then I need 2 zincs. So does that balance? Yeah, that gives me 6 oxygens, 2 zincs, and 2 sulfurs. Okay? So because I could balance it, that is the right answer. Okay? All right, and this one is going to cause a little bit of an issue. We'll see if we can figure out the issue. Bismuth is heated strongly in oxygen. I'm going to make a bismuth oxide compound. What can you tell me about bismuth? Solid, yeah, but what kind of bismuth oxide am I going to make? Strong? No. Go back to nomenclature, guys. If I put bismuth and oxygen together, what was the requirement for the name? Okay, let's do this. What's the formula for bismuth oxide? Why? Why Bi2O3? Why not Bi2O5? Y'all are acting like you've never seen things with more than one charge before. Bismuth can have more than one charge. Is everyone on that same page? Okay, does everyone see that? It's a problem. We need to know which one we need to make. Okay, So does everyone know that what bismuth's possible charges are? If not, you need to remember, what are the possible charges for bismuth? 3 or 5. So the question you ask yourself, okay, which is it? Last year, you learned a little saying. As Stan fell, what happens? Huge cups cracked. Okay, if it's in this saying, these elements prefer the higher of the two oxidation states: arsenic, tin, iron, mercury, copper, and chromium. If it's not in this saying, you go with the lower of the two oxidation states. Is bismuth in this saying? No. So we're going to go with the lower, which is a +3. So what would be the formula of bismuth 3 oxide? Bi2O3. And so oxygens, we need a 2 there and a 3 there, and then we need 4 bismuths. Okay, so if you're ever combusting any element like these that all have different multiple charges, you're going from the 0 state to some sort of positive number. That's going to be a charge change. That's why it's redox. And you're going to have to figure out, well, which charge do I go to? And that's based on as Stan fell, huge cups cracked. Okay? All right. So as far as what you might see for the alkanes, if we give you combustion examples, you guys are responsible for knowing all the alkane formulas for the first 10 carbons, from 1 carbon to 10. So methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. And you need to know the formulas associated with those. If you want to memorize that the number of carbons is equal to 2 times the number of hydrogens plus 2, you can. Or on the side of your paper, if I'm telling you you need to combust butane, you could be like, okay, I know but is 4, and I know it's full of hydrogens. That's 6, 7, 8, 9, 10. So it's C4H10. You don't necessarily have to memorize the formula, okay? But I do want you to know the alkanes and the cyclos. With the cyclos, the formula is different because you're attaching them in a circle. So 2 of the hydrogens go away, and so it's just 2N for the cyclos. But I want you to be able to know the formulas for all alkanes and at least the cyclos. We're not going to give you the alkenes and kinds. I do want you to know what they are. Like if you looked at a compound, I wanted you to be able to recognize if something's an alkene. An alkene is just something with a double bond in it. You use the same prefixes, methene, no, there's no methene, ethene, propene, butene, pentene. If there's a double bond anywhere in it, it's an alkene. Alkyne, same prefixes, just the YNE ending, and the difference is there's a triple bond in there. So these I just want you to know for identification purposes. These I expect you to be able to give the name or the formula back or forth. Okay? Got it? All right. This whole complex ion thing we're leaving out, so you can scratch out the rest of your notes through the unit, actually, because today was officially the last day of the unit. Like, all this is not going to be on there. Yep. So that was the end of the unit. So your homework tonight and over the weekend, you've got 2 things you got to get done. You've got your standard homework, which is really important. The reactions are all mixed up. We have a day where we just do a quiz and grade it. That's how much students struggle with this. So I'm trying to tell you now, take that homework really, really seriously. And then you have a pre-lab you need to do. Part of the pre-lab is to watch a video. I made a pre-lab video yesterday because today was a shortened pep rally schedule. I wasn't going to be able. It's like a 15-minute video, and it's going through all the equipment and all the calculations. So watch that video before you even do the pre-lab, okay? And then after we do the lab, it's quite it's like a 2-part lab. If you forget how to do the calculations, watch the video again because it tells you how to do the calculations, okay? All right. Come see me Monday if you need help on any of those problems, or if you hit a problem right now that you're having issues with. We can talk about it.